Hello everyone, welcome to today's presentation where we will dive into our problem statement, that is terrain recognition using convolutional neural networks or CNNs. We are very much excited to show you how our model tackles this critical task. We will use the dataset from kaggle.com which consists of 35,000 plus training images. So this is the dataset which consists of the train images and it also has mask images. Here are the mask images. It also has some validation images. Here is the validation images. And it also consists validation mask images. For doing this project, we are going to use this following technology stacks such as Anaconda, Jupyter Notebook, TensorFlow, OpenCV, Node.js, Python, Pandas, NumPy, Keras, Kaggle and Matplotlib and many other. Now here comes the part of data processing. First we will use patchify images. The main function of patchifying images is to enable more efficient processing and analysis of large images. Large images can be computationally expensive to process, especially in deep learning models like convolutional neural network. Now by dividing the image into smaller patches, we can reduce the dimensionality of the data, making it more manageable for the model. Here is some code snippets of the implementation of patchify. Next we move on to normalizing images. The main function of normalizing images is to preprocess the input data in a way that facilitates training and improves the model's performance. Normalization often involves subtracting the mean value from each pixel in an image. This centers the data around 0, which can help prevent gradient vanishing during training. Centered data makes it easier for the optimization algorithm to converge to a solution. After centering, normalization typically involves dividing the pixels value by the standard deviation. This scales the data, ensuring the features have similar orders of magnitude. Scaling helps prevent some weights in the neural network from dominating others, making training more stable. Next we move on to rendering images. Rendering images typically refers to generating synthetic or computer generated images. When real training data is limited or expensive to obtain, rendering images allows for the creation of synthetic training data. Next we move on to RGB2 function. The RGB2 function specifically in CNN is to convert RGB color images into label maps or segmentation masks. Its main function is to map each pixel in an RGB image to a corresponding label or class identifiers, effectively converting a pixel-wise classification problem. Now we see that the left image is of the satellite image and the right image is processed labeled image. Now we will start data augmentation. It is a process which artificially increases the dataset by modifying the copies of existing data or synthetically generating new copies of the dataset by using the existing dataset. We then split the dataset into training data and testing data. We chose the UNet model for training the dataset because UNet is well suited for multi-class image segmentation tasks as it can handle a large number of classes and produce a pixel-level segmentation map for each class. Then we will move on to the preparation of the UNet model. We have used IOU loss function, which is known as intersection over union, which is commonly used in image segmentation tasks, especially in situations where objects of interest have irregular shapes and there is a need to measure the overlap between predicted regions and ground truth regions accurately. On the left side we see the images from our dataset and after processing we see the predicted images on the right side. Next we build the confusion matrix. A confusion matrix provides a concise summary of how well a CNN is performing in terms of classifying different categories or levels. It breaks down the classification results into 4 key matrices: true positives, true negatives, false positives and false negatives. The confusion matrix is used to calculate the overall accuracy of the CNN. Accuracy is one of the most commonly used performance matrices and is computed as the ratio of correct predictions to the total number of predictions.